So let's start here. Here's our problem to solve. We're going to take a number as an input, and this is almost verbatim code the way I wrote this out. And we're going to see if that number is a 0, and if so, we're going to output a 0. And if not, we're going to output a 1. So essentially, we're just looking for a 0. If it's a 0, it's a 0, otherwise it's a 1. Now, let's start with the high-level code. Since this one is just really obvious, so I'm just going to go ahead and write it out. So I'm going to have an integer, and I'm going to call it number, and it's going to be provided to me by that magical function called input that we talked about. Just to kind of quickly recap, remember when you're doing something like system.out.println in Java or pick your language, right? Write in C, you are using effectively what's called a system call from your operating system to enact the system displaying your output. We're actually going to talk about that more today when we get to real assembler in 6502. To abstract that into oblivion, because we can't deal with it at a negative level, I'm just using a function called input, right? An output function will provide output. So that gets me my number, stores it. Now I have to do the if part. So that's pretty straightforward. If my number equals 0, output 0, else output 1. All right. Everybody agree with this? Is this a good program for intro to programming? Cool. All right. Now, let's take our intro to programming up a notch. How are we going to make this into assembler? Where's my first step? Yeah. Output? Yes. Or input, right? We need input. When we look at this first line, we have to start here on the right-hand side before we can deal with that. So on our little bin assembler here, we're just going to ask for input. Now, how do we deal with the second part of that? What do we do there? Put little min. Yeah.
You store the input in a variable, I guess now.
Yes. So that's a good call too, because we are going to use labels at this point since we're fully developed. They were introduced in the last video in the series. I'm going to store it in something called num. And as you'll see as we go through this label is later going to reference a line number for me. And when we assemble into instructions, we do that one-to-one, the assembly process, I should say, is going to fix it for me. It's going to take that label and make it into a line number, which we will see. So we know we're going to store it in num. This is analogous to us naming a variable in high-level language. All we're doing here is naming a place in memory where we're going to store something, right? That's all we're really doing here. I mean, we add types in a high-level language. That's important to us, types. But what we're doing really is picking a place and naming it that we're going to store something. All right, so now we've accomplished line 1. What do we do next? This isn't always clear-cut, depending on the branch and what we're trying to accomplish. But who wants to take a stab at our next line? Yeah.
You possibly, I guess, maybe branch down to the if statement.
So, well, yeah, so the branch will be, the if statement will be the branch. You're seeing like branch down to a particular line, or?
Yeah, I don't know. I was thinking have like a branch on positive or something down to a branch on 0, and then have all the if code in the middle between.
Well, if I have, let's start with the branch on 0. If I have the branch on 0, I think that actually makes my decision for me, right? Because here, if I have a branch on 0, that actually means that I can go here, and if I don't branch on 0, else fits the bill for that, because it's not an else if, right? So I think branch on 0 is actually all I need. So BRZ, branch on 0. Now, the interesting part about this is, unlike our high-level code, as we just noted, we're branching if this is true, right? So your intuition might think you're going to the next line here to deal with 0, but actually you're kind of flipping it. You're going to branch down. The next thing you would deal with if you don't branch, like I'll pick a label here as a placeholder. Let's call it 0 out, just to denote that if I branch, I'm dealing with 0, right? But if I don't branch, I'm effectively dealing with this first. So on my next line of assembly here, what do I do with this? Yeah.
Output 1.
Yes, but what's 1? Yeah.
It's just like a cat value or.
Yes, that's very good. So notice here, we just kind of typed a 1 here. We didn't give it much thought, but a 1 doesn't actually exist in the purview of our program until we give it to you. This is actually a constant. It's like a final. It's something that you're not going to change in your code. You just typed it, right? It's not variable, but it's there, and we have to store it. So the first thing we need to know is what is 0. Now, because we're using labels, we don't have to know where it's going to go just yet. We just need to know that we can get it. So in order to get it, we need to load it, right? So we're going to load it from somewhere. We don't know where yet. So we have our load. Going to load, oh, not 0, sorry, 1. And now that I've loaded a 1 into the accumulator, I can output it, right? So now these 2 lines take care of that guy. Because in order to output a 1, I had to have a 1. The thing that was in the accumulator, remember, we're not sure. If it was a 0, well, that might be straightforward. We'll get to that in a moment, because I want to output a 0. But the alternative is that it's anything else. So let's say they typed in a 4. Well, they didn't say output what they typed. They said output a 1. So we actually have to define the 1 and bring it in. All right. Now this is where things get a little bit interesting. What do we do now? So we're here. We've accomplished this line. What do you guys think? There's a bunch of options. Not necessarily wrong ones. There's better ones. What do you guys think? Yeah.
Output 0. Or output none.
Output, well, output 1 happened here.
No.
Oh, no. So, well, oh, okay, I see what you're saying. So is that because you're saying I'm going to branch to it? Yeah. Okay, that's good. So you want to have basically here, now, but do you need another line for that, or are you just going to reuse this one?
Probably another line. You can reuse that.
We can reuse that one, yeah. So your thought was a good one, because if you think about what happens here, let's try this. I'm gonna throw this up on the board and say we're done, except for the data. Here's my thought. If I have a 0, it says, let's imagine that 0 out is here. That means that I have the 0 already in the accumulator. It's a 0, I branch, I go to out, I home. If it wasn't a 0, I load a 1, I output it, I home. I'm good. That's, I think, the most efficient way to solve this problem. You could have done a halt here, and then had another line for load. You wouldn't even have to load the 0, but another line for output and another halt, right? And then branch down to the second output. You could have had a branch absolute to a halt further down, and then had the output in the middle. But this is the best way to do it. This is the most efficient. Now, the only thing we're missing here is we gotta rectify these labels, right? So we gotta rectify that one, and our 0 out. Our 0 out, we know is here now. So the way you do this is like this. Right, so now I'm saying where 0 out points to. We now have num and 1. I'm going to store them this way, so we use the dat mnemonic. We'll talk more about that in a second. But we use the dat mnemonic and num. To just kind of denote that there's data going here, But one of these requires something that one doesn't. Which one is incomplete? The one, right? Because I need the actual value. So what you have to do, and this is the important part, is for anything that's a constant, final, whatever, you're giving the value with your code, it has to actually go in there. Now, when we bring this across, let's quickly, just for our own sanity, let's give these line numbers. I mean, you probably would have if you were really doing it in Assembler anyway, but just to help us keep stuff straight. Right, so there's our line numbers. Now when we assemble, we just go straight across. Input comes over, that's a 901. Store, what's the opcode for store? That's the one that can be hard to remember. 2. No, 2, not 2, because 2 subtract.
Store in memory?
3, I think I heard it online. It's a 3. So the way I always remember store and load is that I can't load it until I store it. So store comes first. So the 3 is first. All right, so I can't get it out of memory until I put it into memory. So that's how I remember it. So the store is the 3. That's the first one that has to happen in my head. That's my little association trick. Now, how do I get its operand? Stumped everyone. Oh, it's quiet. What did we say about the label? What do we do with the label when we assemble? Yeah.
Bring it over.
Yeah, so we look to see what line number it refers to. So what the assembler actually does is it just says, okay, you're referencing a line called num. Where did you declare num? You declared num on line 7, so it just takes the 7 and sticks it in there. Because remember, the actual machine instructions know nothing about labels. There is no more abstraction. We are at the bits, right? No more abstraction. That's abstraction, believe it or not. It's a simple abstraction for us humans, but it's an abstraction of line numbers. We have to rectify it, so we do. Second line here, well, third, but it's number 2, is our branch on 0. So branch absolute is 6, branch on 0 is 7, branch on positive is 8, right? Those, I try to remember them in that order because they kind of like grow in importance, I guess, or the amount of values they can branch. But 7 is what we need. And again, we use this 0 out to figure out what number we want. So we want 4. Yeah.
Order around this 7, 8 for branches.
Yeah. So the order was 6 for branch absolute, 7 for branch on 0, and 8 for branch on positive. Now, to me, it's like increasing order of, well, I guess it's not, it's a conditional, like in 6, anything branches, it's an absolute. But 0 is less than positive because positive includes 0 and all positive numbers. So I just kind of think of it that way. If you remember, absolute comes first, then 0, then the bigger one. All right, so 3 is a load, so that is a 5. And we're loading 1, which is in line 6. So we get 506. 4 is our output, so that's our 902. 5 is our halt. 6, remember we do care about this because that is our data. So what we're putting here is actually just 001. Remember, stored program concept clearly states that we can put whatever we want in these mailboxes, instructions or data. It is our responsibility as programmers to know where they are so we can branch around the data if we don't want to stumble into it as an instruction, right? But we have to put it there. The other one, now, I'm not going to mark you wrong for leaving it blank. You can put 3 zeros here. At the end of the day, when the input happens, and the value is stored here, you're going to overwrite this. So if it means you're just making a mess of your paper because you're crossing off numbers, don't bother to put the zeros, just leave it empty, and then you can put the value in and fine with that. But in reality, it was likely initialized. All right. Any questions on that part? Everybody feeling pretty good? These are the kinds of things that you will see on the quiz and you will see on the midterm. Okay. Maybe with more complexity, but same idea. Now, the little man dance, I'm not going to do here. I did a lot of the videos, but you know, any questions on the little man machine? The instruction cycles, big part, fetch, decode, execute. Anything there? Okay. I'll try to point out some differences in these things as I now shift into 6502. All right. Let's do that. All right. Do you guys see my share now?
Yep.
All right, good. Make it a little bit bigger so everyone else can see it well. And this bigger. All right, I'm not going to jump into the instruction set just yet. I just wanted to get it ready. I am going to, let's see, can I do, sorry. Okay, so I want to talk a little bit about the 6502 processor now, mostly because there are some things you need to know to fully understand this instruction set. So the differences, let's start there, between the little man, actual physical machine, which you know is a metaphor in heads, but it does represent a physical machine, is that we have more registers here, right? A lot more than I'm going to kind of describe. So let's start there. So in little man, we had an accumulator, we had a program counter, and the in and the out box are actually analogous to I/O registers, but we didn't really talk about that. That's about it. We glossed over, there's usually registers for the memory address and the memory data. We didn't really talk about that. The little man just kind of got the thing out of the mailbox magically. But we'll talk a little bit more about that stuff now. Let's start with just the accumulator. So we have an accumulator here, luckily. So here are the registers that we have in the 6502. We have an accumulator. We have an X and a Y register. Now, these three are what are known as general purpose registers. We can use them for whatever we want as programmers. We can put information in there, just like you did with the accumulator and little man computer. The accumulator and the 6502 actually.
Hey, Professor?
Yeah.
Can you turn the screen share off just so we could actually see the board?
Oh, yeah, sure.
Instead of the optical. Yeah, thank you.
There's not much on it, just the registers. But remind me and I'll put it back if I forget when I go back to the instruction set. So these registers now are general purpose, right? The accumulator, that's where I left off. The accumulator is just like you can put a value in there. You can then, it's kind of weird, I can see myself on the projector, so I walk around. You can put it there. You can then add another value to it that might be stored in memory, and the result is going to go back into the accumulator, right? So that is the same as what we expected in little man. X and Y have some simple, sometimes incrementation. They can increment maybe, but they're not tied to a full ALU like the accumulator is. So you're not generally going to use them for math. They're little scratch locations where you can stick information. They have some really important purposes that we'll discuss as we go through our instruction set, but they are also general purpose registers. We also have a program counter, just like we do in Little Man. We have something called a status register. The status register is 8 bits, but it actually only uses 7 of them. If you remember, we had a branch on 0 and a branch on positive. These were all done by branching on conditions that are called flags. These flags are set when information goes through the accumulator. So if, for example, you put something through the accumulator and the result is 0, that would set a 0 flag. Then if you wanted to branch on 0, you could check that flag, right? The status register is where we put those flags, okay? So things like checking for 0, we're gonna come back here to look. That's gonna be the important one. I did whittle down the branches. We don't have the entire 6502 instruction set, we have a subset of it. We'll talk more about that as we get there. Yeah?
The Z flag in the status register?
The Z flag is in the status register, yep. So when you want to check to see if 0 was set, you check the status register. There's also a stack pointer. Now, this is here at this point for completeness. It is not something that we're going to talk about today. So, and there's actually a memory address register and a memory data register. I'm going to get more to that in a moment. But the stack pointer. There is one big aspect of low-level programming that we have not addressed. You probably have noticed that none of our programs have involved recursion. None of them have resulted from functions calling one another. We're actually going to touch on that a little today as a system call, but not quite the same thing. In order to move from a stack frame to a stack frame, we need a stack pointer. When you call, if you've ever looked at the kind of garbage spewed by a Java stack trace, right? What you're looking at is all the functions that were called from the very first function to the one that you were in. And the one that you were in where you had the error, you went all the way up the tree, right out back to the top. So from the very first function that ran, that called another, that called another, that called another, that called another, and finally where you blew up, right? The reason for that is because every time you move scope from one function to another, you're sticking a reference on the stack, which remember is the first in, last out data structure, that then allows you to go back, right? So you can find where you left off. Computers work this way. So that's why, by the way, when you pass something into a function, that's why scope exists, right? Because it's part of that piece of the stack. If you're not on that piece of the stack, then you better make it global, because it has to go in the heap. Different discussion for another day. I'm not getting in the stack pointer yet. We're going to get to that later. It's just too complicated at this point. But I want to address it to let you know that I didn't neglect it. It is there. We're just not doing the stack yet. That comes later. All right. So those are our registers. Now, one thing I want to discuss before we go any further is their size. Anyone remember how many bits the 6502 was? We call it an X-bit computer back in the day, or N-bit computer. Does anyone remember how many bits were 6502 was considered? It goes back to the glory days of like Nintendo, Sega. Yeah.
Is it 8-bit or is it?
Nope, it's 8-bit. Yep. No, it's an 8-bit computer. So what does that mean? That means that the word size, or the amount of data we work with at any given moment, is 8 bits. That means that these registers here, your accumulator, your X, and your Y, these are all 8-bit. Your memory values are 8-bit, right? So what I store in a single location of memory is 8 bits. The range on that, anyone remember? What's the range in decimal? Or any? Yeah.
0 to FF.
0 to FF, which in decimal is 255, which is 256 is the range. Perfect. So that means that if we have a value bigger than that, we need multiple memory locations to deal with it, right? That's a different problem. But that's what a word size is. A modern computer is usually 64 bits, right? So we have a 64-bit word size. We store 64 bits in a single memory location. We have 64-bit registers, right? It's grown a lot. But here we have 8. But, as we discussed early in the semester, we need more than that for memory. Because if we address memory with 8 bits, that means we only have 256 places to stick crap of 256 size. And that's not a lot. So we need more. So we have a 16-bit memory address. What does that mean for our program counter? How many bits do you think this guy is? Remember what the program counter referenced in Little Man? It's 16. It's 16 because it has to be able to reference any place in memory, right, to get the information out of it. Remember, the program counter is where we look to find our instruction. So this is 16-bit. The status register, like I said, is an 8-bit register that they use 7 of. It's back pointer, don't worry. We're going to get to that later. Yeah.
There's 8 bits for itself, 8 to store whatever the other value is.
Nope, it was 16 because we had 16 bits worth of memory addressing. So if I had memory address 16, that actually looked like this in hex. Right? Because in hex, each of these is 4 bits. So my actual address is okay. That's memory address 16. And I need to have all 4 of these because I have that much memory address space. Now, you didn't have to physically use that much memory address space, just like here today. Hypothetically, a 64-bit computer can have exabytes of memory. You want to have exabytes of memory? I sure as hell don't. But a 32-bit computer, anyone know how much memory you're limited to? Theoretically, without any software hacking.
Terabyte?
Nope, much less. Any takers? Yeah.
32 gigs.
Well, so not 32 gigs, but 32 bits would be 4 gigs. So the quick way to remember that is if you remember every 10 bits gave us, a kilobit, megabit, gigabit, right? So if you have 30 bits, you're up to gigabit. Then you have 32-bit, so you have 2 more bits. 2 bits gives you a range of 4, so you have 4 gigabit. Now, you might say, well, Windows only ever gives you 3, and not that you guys probably have any 32-bit computers, probably so you don't know that. But the reason for that was just Windows, because it was Windows. But no, there were, other versions of like Windows Server that I think could get all 4 gigabits. But that aside, the theoretical limit was that. And 64 gigabits is in exabytes. So, yeah, 16 exabytes, I guess. All right. So now we are, I think, ready to talk instruction set. That's pretty much what we need to know about hardware to get ourselves going. I'm going to flip you guys now back to now, by the way, there's more that limits your memory than just how much you can buy and how much they stick in a single DIMM. So as you'll learn as we go through this more in the coming weeks, your memory address bus itself has to support the number of bits that go to the memory. So not all memory addresses actually. All right, can you guys see that now?
Yep.
Awesome.
Yes.
Not all memory address buses, I don't know if any, even supercomputers, actually have 64 bits addressing them because no one's actually putting exabytes of memory in their systems. So the physical size of the bus, these lines etched across the actual silicon and the motherboard have to be large enough to support that. And your opcodes, you know how like in Little Man Computer, how we had the operands that were attached to the opcodes that signified what address and memory we wanted to store something and load something into. That would also have to be 64 bits in size to talk to any part of memory, right? Which that isn't the case either. So 64-bit computers are limited by a lot of things, not just the physical RAM that you stick in them. All right, so let's now talk about this. This is our first real-world assembler. It's our 6502. It is the virtual machine that you will be building as part of your lab project. There are a lot of similarities here, and there are a lot of differences. I'm going to hit you with a lot of stuff today that is going to be new and hopefully exciting. But I'm warning you now, try to be as alert as possible. There's a lot to unpack here in a short amount of time. So I'm going to start with just what's at the top of this sheet. So we have the description of that I'm going to get into. That's obvious. Description is a description. The opcode, let's look at that. So for each of these, I have an opcode and I have a mnemonic. The opcode is obviously what's going to be our actual instruction. So if we look at these and we say, and don't worry about the board for this, guys, I'll try to say it out loud, but I'm just writing out the bits to express the text here. So I have A9, right? All that means, remember, is that an A binary is 1010, and a 9 is 1001. So those are the actual bits that would be stored in memory or put into the instruction register or dealt with in some way, right? So that's all A9 signifies. It's just an easier way for us humans to remember what's going on than looking at that string of bits, right? The mnemonic is easier still. We like load better than we like A9. Now, load A, we didn't really talk about this, and this is why I like LDA and STA over STO, which little man, sometimes people use that there, I don't like it, because what it literally means here is load accumulator, because now we have more registers, right? And that's what you're doing in little man anyway, in accumulator. So that's what that means, load accumulator. Now, the assembly. Here we're looking at the mnemonic for the opcode, plus its operands. Now, let me talk a little bit about the operands. What's different here, in Little Man Computer, you only ever had one, if it was important at all. Now we can have 0, 1, or 2 operands, depending on the instruction. There are different reasons to have different amounts of operands. The symbols here, the $sign, I'm going to start with that one. That just denotes hex. All of these are given in hex. The $sign just means as a hex value. That's all you need to know. It's just assembler convention. You could actually denote different bases. We are only ever going to use hex. Keep it consistent. The number sign, however, the pound there, hashtag, whatever you want to call it, that denotes that it's a constant value, sometimes called an immediate value, that I'm giving with the instruction. All right? Unlike Little Man, in Little Man, we didn't have that. If we wanted a value, we had to get it as input, then we had to store it, right? And then we could go get it. Here, we don't have to do that. We can actually give the instruction with the value. Say, you don't need it as input, here's the value 7. That's yours now. Okay, go stick it in the register, or memory, or whatever. So that's what that is. So I'm saying, take the value 7 and stick it in the accumulator. All right? Now, let's look at the second line here. Same idea. Load the accumulator from memory. Different opcode, same mnemonic. Now, the eagle-eyed among you might be like, hey, Gorman, you told me not all that long ago that assembler was a one-to-one relation with an instruction, and that there was a direct translation. So how do I have two of the same mnemonics for different opcodes? Well, that would be a very astute observation. But the truth of it is that they are, in fact, the same thing. What's changed is the amount of opcodes and what I'm loading. So I'm still loading the accumulator. It's just whether or not I'm loading it with a constant or I'm loading it from memory. So that is why that's okay, because it still translates in the end to something different. So here, what we're saying is load from memory. And where in memory, just like this is analogous to the full man load. All right? Where in memory is the memory address, which we said before we need 4 hex digits to represent because it's 16-bit. We get 4 bits of hex digit. Yes?
So since it's loading from memory, that's why it doesn't have the pound sign, because the first one was a constant.
Correct.
Result.
Correct. So the pound sign means that this is a constant. If you get value I'm giving you, it's not something you're getting from memory. If you don't see the pound sign, I'm referring to a memory address. The dollar sign just means hex. That goes both ways. Now, you also might think I have a typo here. Because you might look at this and say, load 0010, AD 1000. Wait, what just happened? That's backwards. Right? It's not a typo. Not the typo. Alright. What you were looking at is what is called Little Endian memory addressing. So what this means is that I'm going to take how many bits in a byte? 8. That's correct. So how many hex digits represent a byte? 2. Yep, 2. So for each of these 2 hex digits, I have 1 byte. So I'm going to take the low order byte, and I'm always going to reference it or store it first. So whenever I'm talking about a memory address, or I'm storing something in memory, I'm taking it and flipping it. So let me explain. And I'm going to describe this for you guys online. So what I'm doing here is I'm simply writing out 16 as binary in 16 bits. So here is the number 16, right? Hopefully I got the right number of zeros. It should be 4, 4, 4, 4, and 4. Yep. What I'm saying is that I'm going to take this, which is the low order byte, the bottom half, and I'm going to store it and reference it first. So what I'm actually doing is taking this part, and I'm putting it before this part. If I kept it the way it was, it's what's known as Big Endian. This is Big Endian, keeping them in order. This is Little Endian. Now, why do I want to do this madness? It's actually just to drive me nuts. That is literally the only reason. No, I'm kidding. It's really because, especially back in the day, 6502 was the coolest thing in town. Memory was extremely expensive and obviously very rare because you can tell we don't have much of it. So there are different addressing modes. We only actually talk about 2 or 3 of them, but there are 13, I think it's 13, 12 or 13 for the actual 6502. And not all of them require both bytes to talk about memory. So we'll actually see this later when we get to branching, but there's the idea of relative addressing. And what that means is that instead of addressing the whole memory space, I'm going to address half of it. So what I get is 256 memory addresses from where I am. I don't get access to all of it if I'm using relative, but maybe if I have a loop and I need to reference something that I know is like 10 lines of code away from where I am, I don't need to reference the whole thing. I can reference relative to where I am. Just like a link is relative, right? Instead of an absolute link. Same idea. Now, why do I do that? Well, I do that because it means I don't have to store both operands. I can store one operand, which means I just take up less space. I take up less memory. If I'm using Big Endian, I still, because I store this first, oh, sorry, this was Big Endian. Because I store this first, I have to store both, right? I have to still have that as a placeholder. But if I'm using Little Endian, and low order byte comes first, and that's all I need, then I can just go on to the next instruction, and I didn't have to worry about the high order byte. All right? Here's the trick. Anytime that you're talking about memory, storing something in memory, or referencing a place that you stored something in memory, you have to flip it when you're writing it in code into Little Endian format. But understand, when it goes into the register, you're actually seeing it in the register, it's put into the right order in the register. Register doesn't see it in the format. It is stored in your code, like the actual operands are stored in little Endian format. Okay? So the operands for your instruction that are memory addresses are stored as little Endian. Everybody okay with this? I wasn't when I first saw it. Alright. So that's that. Now, let's talk about these different loads and stores. So here's a store. Same idea as what we saw in Little Man. In fact, this one is just like Little Man's store. It's store A, so we're storing in the accumulator. We're storing from a memory address, exactly like we did in Little Man. It's just that we're not using 3 decimal digits to address memory. We're using 16 bits or 4 hex digits, right? In Little Endian format. So that's all this is. Now, let's come down to here and look at these different ones. Notice here we have loads, but this time we're actually loading from one register to another. So I have load the accumulator from X or load the accumulator from Y. And notice here that their mnemonic is TXA. T stands for transfer. So anytime you're moving from register to register, you're not loading or storing, you're transferring. Right? So if you see that T, it's a transfer. What am I transferring? I'm transferring from X to A. I'm transferring from Y to A. Right? A is equal. Same thing happens down here. I have some more of those, like down here. Load the X register from the accumulator, reverse it. It becomes X. Load the accumulator from X. Or transfer accumulator, I should say. Notice these don't have operands. I'm not asking you to load it with an immediate value. I'm saying transfer. It's going to take whatever the value was in the first one, like X, and move that value to A. Right? So there's no operand. I'm not addressing memory. I don't need to give it a value. The value is already in X. And now it's going to be in A. Right? All right. The add, this is also just like little bit, believe it or not. Same idea. It's going to take the contents of the address that we have the operands, and the value out of that will be added to the accumulator, and the result will, again, reside in the accumulator. So if we added 2 in our accumulator, and we have memory address 16 here, because remember this is little Endian format, so you put the high and low order bytes to look at it correctly. So in memory address 16 is the value 3. The result's going to be 5, and it's going to keep that in the, just like Little Man did. All that really changed here was how we dealt with the address, right? It's just now in little Endian format, and we're using hex to denote it instead of decimal. It's a bigger number. All right. Any questions so far? Loads, stores, transfers, adds. Yeah.
I said one.
Sure.
So when you're loading it, considering like actually loading X number 7.
Yes, that's exactly right.
From the mailbox X10, or is that the number of X10?
So, where are you looking at the X10?
The load at the top. So this guy remember.
So, okay, so the 10 here is, remember this is little Endian format, so they flip. So it's actually 0010 is the actual memory address, so it means in memory address 16.
Is it the same as like the mailbox?
Yep.
And is the constant like mailbox, or is that
The constant is constant. So that one just means I'm going to load the accumulator with 7, the very top one. This one means whatever's in mailbox 16, that's going to load there. Just like that one, this one has no representation in the man. The constant, this one does. That one's the same. Yeah.
So sorry, I was just a little, so for the binary column, the first term is on the 2 load and store. The first term is hex, but the next 2 are binary.
No, they're all hex.
They're all hex.
Yep, this is the hex. This is the hex number 16 in little Endian format.
Got it.
So it's really 0010, which is 16, and because you take that, it's right here. It's actually this, right, which is 16. I'm just representing it in hex. I know it's confusing because the column is called binary, and we're representing it in hex, but that's just for shorthand to keep ourselves safe. because otherwise that column would be the entire page, and it would make no sense. So that's all that is. Yes.
Hard to trust that verify. So it'd be on Endian is it on the Accumulator version when it's actually flipped.
Yeah, so the one that's flipped is, these are flipped, these are little Endian format. This is regular. Always, I keep that consistent with this form. Okay? All right, and the reason for that is when you write the assembler, it actually figures it out and flips it for you. But unfortunately for you guys, you're not going to read the assembler. We don't have a 6502 assembler that works with our machines anyway. If you want to write one, that would be a cool extra credit project. But we're going to be directly writing our programs with the outputs. Okay, so I'm good here. I'm going to scroll down now a little bit. Because like I said, there's a lot of loads, stores, transfers. It doesn't really change, other than that add, doesn't really change until we get down here. So I'm going to address these now. So the first one is no op, and it is exactly what it sounds like. Don't do anything. Now there's a few reasons for this, and most all of them come down to the time period in which we're building these chips. These things came in 1, 2, or 3 megahertz speeds, and that is true. That means that they were either baseline, double as fast, or triple as fast. So if you wrote a program for them and you were running on 1 megahertz versus 3 megahertz, you could get completely different outcomes as far as how fast the program ran. That might be good or bad for the program. We didn't have multitasking back then, or any other kind of mechanism like a event-based UI to slow it down. So you might have written in no ops just to slow crap down. That is a possibility. The other big one is that you also might have been waiting for IO or some kind of message or something, and you also didn't have a operating system to manage that for you. There wasn't always an interrupt-driven system. We're going to talk a lot about polling versus interrupts in the coming weeks, but for the most part, you were in a polling situation. So you might have sent out a message and you're waiting for a response, and you might have to sit there and wait for a while, check to see if you got a response, nope, wait again, right? So no ops might have been useful. Break is halt. That's the same thing. There's nothing really notable or interesting about them, other than what they are. I don't think you'll honestly have to use no op in this class. You're welcome to if you think you do. If things are slow enough, as you'll see. I don't think we need to make them any slower. Break is, that's false. And you'll need that one, but there's nothing really monumental there. Now, these get interesting. So, I have one branch here. We only going to need the one to save us on sanity, and honestly, it gets the job done. So, what we have here is first a comparison. So, this EC instruction here, or CPX and assembler, is to compare X, right? That's what the CPX is. So it compares a byte in memory to the X register, and it sets the 0 flag if equal. Now, it's important to note the terminology here. Sets the 0 flag means the 0 flag will be a what? What bit will be in the 0 flag, do you think? 1. So it's a little deceiving, right? You're thinking 0, right? Yeah, exactly. So you gotta read through this and like think about it. So wait, so let me get this straight. I compare it, and if I get the same, then I'm gonna set the 0 flag to 1. Okay, but that's what it is. Then here, on this instruction, I'm going to read the 0 flag, and if it's a 0, which is the opposite of what I said here, right? So basically it's going to be a 0 if this was not true, then I'm going to branch, right? So you got to keep all this stuff straight in your head as you're going through it. This is checking the 0 flag. I deleted it in that status register that I had before. And if it's set to 0, I branch. Now, this is interesting, because look at this operand here. So I have D0, EF. Now, if we read the description here, it says n bytes if Z flag is 0. So EF is a pretty big number, right? I mean, granted, I only have a relative address. I only have the low order. But you know, we're looking at like 240 or something. It's something big, right? If I figure that out, so E is this and F is that. It's a big number. So do we think we're jumping that far or not? Let's look at this real quick, and I'll describe this for you guys on the call. I'm just putting some simple line numbers up here, starting with 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3, 4, 5, 6, and 7. So just imagine that there's zeros and those two in the middle. And let's say we have a program running here. And I'm going to have a D0 call here. Now, first thing that's important to know is that I put the D0 on line 5, right? First thing you need to know is that, remember, memory values only have 1 byte in size. So I don't get to put D0 and its operand in here. I only get to put D0. Guess where its operand is? The operand is down here, right? So let's put, I'm not going to put the EF, I'm actually going to change it to keep it smaller. I'm going to make it smaller by making it bigger. I'm going to put FC. I'll explain why in a moment. Now, so what happens here? Well, a couple of things I want you to realize. One is, remember in Little Man Computer, when we got an instruction, we fetched it, we decoded it, we executed it, we incremented the program counter, right? That was the order. Well, a real computer is a little bit different. There's one big difference I gotta get out of the way first. The program counter does not get incremented at the end. The moment you fetch, like the very moment you go there, you fetch the information out of memory, you immediately increment the program counter without even waiting. Now, why? The answer is because it's an optimization. If you do everything in order and you wait till the end, increment the program counter, you're wasting a machine instruction cycle, just incrementing the program counter. We can optimize by putting a little incrementer on the program counter itself, and then once you grab the thing from memory, while it's executing, in tandem, the program counter can increment, right? So we're saving ourselves a step. That adds up for every instruction, right? So keep that in mind. The next thing to know is that unlike Little Man Computer, our operands are all in their own memory address space. So that means as we fetch an instruction with an operand, we're not just going to get to the next instruction to the next memory address. We're going many memory addresses, depending on how many operands we have. We could go to the next address if it's like a no-op, right, with no operands. We could go 2, like in this situation. Or if it has a full memory address in there, we could go 3, right? So there's going to be a cycle to grab the opcode. There's going to be another cycle to grab the first operand. And if there was more operands, there'd be more cycles, right? So I'm telling you this for a few reasons. One is because you'll realize when you get to building your own machines, you have to manage where your program counter jumps for each type of instruction. But the one that's actually relevant right now is understanding where your program counter is when you branch. Just remember, you have to know how far back you go. So the truth of this one is you're going to get this and you're going to fetch it and you're going to say, oh, okay, I'm going to decode that and I understand it's a branch. A branch has one operand. You're going to go get that. You're going to say, okay, I got my operand. I'm going to hold on to that. The moment you get this thing, you've already incremented your program counter to here. So where you're branching from in this example is line 7 from line 5. All right, so when you're doing the math on like your branch, it's not as simple as Little Man Computer, where it's like, you know, explicit from the place you were. Now you're talking about it's actually from 2 ahead where you thought you were, right? Because you incremented your program counter to get the operand, and then the moment you got it, you incremented it to the next spot. So when it executes, your program counter is here. Now, let's say we want to go back. I made this FC. Why did I make it FC if I want to go back? What have we learned recently that would explain this? Meaning like very recently. Yeah.
You have to swap the values to make sure it's appropriate.
Not that recently. Not little Endian. Not today. What have we just talked about? How do we deal with numbers? Yeah.
It's going to be overflow.
No, it won't be overflow. We're in the right neighborhood though, as far as topic goes. What type of number do we usually use to represent the assigned integer? Yeah. Complementary, specifically 2's comp, right? And that's what we use for 6502 as well. This is a 2's comp number. So what does that mean? It means I want to go backwards because we're in the top half of the range, right? So just like all 2's comp numbers, we split our range in half. It's no longer 0 to 255. It's negative 127 or negative 128, whatever it is, to positive 127, right? So this, let's take the F and the C. What do we do with 2's comp? Flip it. Add 1. And we get 4. Huzzah! We want to go back to 4. Got it? If I wanted to go forward 4, I just would have stuck 4 in there. Right? So I will go back 1, 2, 3, 4. This will set the program counter to 3. Why 3? Not 4 back from 5. 4 back from 7, where the program counter was when it ended. That's an important detail to know. All right, I have one more thing I got to talk about, so I'm going to try to be brisk. System calls. Now, a modern computer does what's called a system call. If you want to, we talked about this just before, system.out.println, right? I want to print something to the screen. My program doesn't want to be the driver for your screen and know what screen you have and all that good jazz, right? I just want to print something. So how does that work? Well, I call up the operating system, a specific API, and I say, hey, I want to print something. Here it is. And the operating system does it for me. That's a system call. Shutting your program, halting your program is a system call. Output, input, all kinds of things. In fact, I have an example here in this document. If you scroll down, this is the Linux system call API for x86. So, which of course is the computer on this desk. Now there's a different Linux system call API for ARM. So the system call API is specific to the hardware and the operating system. Those two things combined give you a unique system call API. Why? Well, let's scroll down a little bit and see. Notice here in this table, across the top, these are registers, RDI, RSI, RAX. Those are x86 registers. So for us, we have accumulator, X, Y. Right? x86 is more. In fact, there's more than this, but that's okay. We don't really care. It's just for an example. In fact, you don't need to know the x86 registers at all. I just need to explain what a system call is by showing you how to perform. So what's happening at a low level when you ask the system to do something or write in C is that you actually fill up the registers with the information the operating system needs and then call the system call. So what does that look like? Let's say I want to write something to the screen. That's this right here. The RAX register, I put a 1 in it. That actually tells the operating system which of these functions I want to run. The name of the function is too big and long. I don't want to mess with that. I just need a number. Number 1, that's right. Number 2, that's where 0, that's read. Open a 5, that's number 2. Right? You put a number in the register. The number you want put there correlates to the thing you want to happen. Think of that as your function name. That's your function name, a 1. Next thing I do is I go to another register. In there, this is just an error code, and hopefully there isn't one. So I'd say put a 0 there, because nothing's wrong. The next one here, this is a pointer. Anyone who can see might know what a pointer is, but I'm pointing to a place in memory where my string starts, because remember, a string takes up multiple places in memory. So I'm pointing to that place. This is where you start. How do I know where to stop? I give you a size. This is the length of the string. right? I put these things in place, my program, I do a system call, I hand over the CPU to the operating system, who finds my things in the contractual location. This is an API, just like any other, and it performs the action I need to perform, and then it comes back to me, right? That's a system call. We're going to talk more about these later, but we need some basic ones to perform some output. So, we have two. We have one to output an integer value, this one here, and we have one to output a string. To perform our system calls, we do the same process. We put in the X register a 1 if we wanted to output the integer, and a 2 if we wanted to output a string. So we have two system calls. That chart had many more. These, by the way, are not part of the 6502 assembler. This is something that we added. We being Dr. Lebsor and myself, and we have slight variations on this one because we have a good party academic difference on how it should work, but for good reasons, so nothing bad there. In fact, this is completely compatible because we just add this version of this system call, it's fine. But this is to address the fact that we need I/O, and we just don't have it. We have this low-level machine, right? And when you get to operating systems, you have system call. So I put the 1 in the X if I want to output an integer, and in the Y register, I put the number I want to output. Of course, that limits me to 256, or negative 128 to positive 127 just use comp. But it is what it is. If you want more than that, I guess you can use this one. For the string, I put a 2 in the X register. I ignore the Y register, my version. I'm sure you don't, but you can get to this class for that. And then here, I have the memory address that I can call. Because I wanted to have all memory. This was our difference. I wanted to be able to address anywhere. This had a relative range of 256, and that wasn't enough for me, so I went this route. So you pick your place in memory where you want to point to. That's where your string starts. When you know your string ends, it's because it ends in 0, 0. So it'll just keep printing until it hits zeros, and then it'll reset and go back to where it was. All right, so that's our system calls. We have two of them. Now, really quick, let me show you this actual app here. So this link here brings you to my version of what you're building. There's actually some code right here, but there's lots of example code in the lab, in that document I was just in, which is linked from your lab. You put code in there, you give this a name, I'm going to call it 2 + 2, and you hit submit. And sometimes you'll see the output. Sometimes, but if not, it depends on how quickly it is and when it polls, because it polls. But if you click the job, you get to see the output. All right. Now, 2 + 2 is pretty easy. Let's look at this really quick. I load the accumulator with a 2. This is a constant. So here's the opcode. Here's the operand. Then here, 8D, I'm storing it. I store it in memory address 16. Notice here that I have little Endian format. So 1000 is 16 little Endian format. Then 6D, I go ahead and add the number back to itself. So I had a 2 that I loaded in, I stored it, I added it back into itself. That results in a 4, right? Then I do this A201. What's that doing? A2, if we go back and look at the thing, but we don't have time, it loads the X register with the constant. So I'm putting the 1 in the X register, getting ready for my system call, right? Because I know I want to output an integer. But I need the integer in the Y register. So A8 moves the accumulator to Y. So that 4 now went from the accumulator to the Y register. Now everything's set up for my system call. I filled my registers with what I wanted. FF is my system call. And that sends the output to the screen. The 0, 0 is the hall. You still need hall. All right. There's more here. So I want you guys to look through these programs. If you go to here, whoops, get out of my way, and scroll down, ignore the assembler. I mean, it's there for your reference, but what you really need is this stuff. You can take any of these. This is Hello World. If I copy it in, get out of the way, and go up here, just put an H here, hit submit, it runs, Hello World, the job will appear over here. You click on it, you can see what happened. Now, we don't have multitasking that happens in operating systems later. So if you run stuff and it doesn't come back right away, it's probably because one of your colleagues is also running stuff. And it does queue it. So you shouldn't have to keep entering it, but you might have to be, a few seconds, even like a minute. I think I have a timeout, like if someone screws up with bad code in there, I think it'll time out in about a minute and then start again. And you'll get an error in the response. And it doesn't necessarily mean that you had an error. There's actually one you can trick me with. There's a powers program that just constantly outputs powers at you. It will do that until it runs out of it hits the timeout, and it'll note that it'll just say error, but it wasn't that the code had an error in that case, it was that you beat the timeout. But it'll also let you know if you have an error too. Yeah.
So will we be building this user interface as well?
No, not in my class. If you take operating systems, you build your own version of it. But this is just so you guys can write programs against mine. And don't try to dismantle it for my code because the front end has nothing. It's all on the back end. Yeah.
So for left, version problem fetching.
Yep. You have to write a full program. So if you read Lab 2, it says do something like a Fibonacci sequence, or it can't be something dull and boring. It has to be something cool, like an actual algorithm that's useful. And you have to do it in little man or not little man 6502 operating. Yeah, and it's going to take some, I'm just warning you, it's going to take some doing, because the hardest part is going to be figuring out where you're branching to, where you're landing. You don't see any errors, you're like completely blind as a bat, so you're really going to have to get pencil and paper out and have some fun with it. Yeah.